Hello everyone. In the first part of this lecture, we will talk about the conditions of optimality or conditions for optimality in unconstrained optimization. So recall that we have looked at this idea of understanding the importance of gradients and trying to move in the direction suggested by gradients to improve the candidate point. So recall our steps are of this form: x I plus 1 is the previous point plus a step length times a direction. And this direction usually comes from the information given by the gradients. If you are doing steepest descent, then S is minus of grad f at xi. But that's not the only direction where function value decreases, and sometimes it is better to not take this direction and take something else. So in general, whenever S transpose grad f xi is less than 0, this direction is okay to move. So my unconstrained optimization algorithm would start looking like this while not converged. S is equal to gradient of f at xi xi plus 1 is equal to xi. Here's a minus, that's a very important thing, plus alpha times s and I equal to I plus 1. So let's look at what is the meaning of this convergence and when do we say that it's okay to stop. So remember that we don't know the shape of the function in general because this function is in several dimensions, but we do have the gradients and Hessians available with us. So if x star is locally optimal, then number 1, the gradient of f at x star has to be 0. Because if it is non-zero, then I can choose S to be negative of gradient of f, like here, and that would be a direction of descent, and I will be able to go to a slightly better point right in the neighborhood of x star. Second is the property of curvature. S transpose the Hessian of f at x star into S must be greater than or equal to 0 for which s, for every s. So here we are talking about locally minimum. What the second condition tells us is that if this condition does not hold, if S transpose grad square F into S is strictly less than 0 along some direction S, then the gradient if the gradient at the current point is 0 and if some S gives us a negative value here, then I can go in that direction and my gradient will start becoming negative and I might be able to find a better point. So and this condition is fairly easy to see in one dimension. So this is really a one dimension problem if I fix S, because I am moving only along S in that case. And this is very similar to your second order derivative test for one dimensional functions. So this part is easy to check. This part is a little bit more complicated because potentially if you go by the definition, then you have to check infinitely many directions, which you cannot do in finite time. But luckily this condition is equivalent to the matrix Hessian at x star being positive definite. So if you have not seen the symbol, this means positive semi-definite. This both combine. And so what is the meaning of a positive semi-definite matrix? A matrix G is positive semi-definite if S transpose G S is greater than equal to 0 for every S. And this is equivalent to saying that eigenvalues of G are greater than equal to 0, all eigenvalues, and there are some more equivalent definitions given in the book. So this is somewhat easier to check than the original condition. So all you have to do is find all the eigenvalues of this matrix, and if they are all non-negative, then this condition 2 is satisfied. Okay, so these are necessary conditions. So every locally minimum x star must satisfy 1 and 2. If these two conditions are not satisfied, then x star is not, definitely not, a locally minimum point. What happens if these conditions are not satisfied? Then x star may still be optimal. Okay, so let's look at those conditions. If grad f of x star is 0, and let's look at the second condition, and then x star may or may not be optimal. This is very important. So that means conditions 1 and 2 that we had written are necessary conditions, but they are not sufficient. And the simplest example is something we are all familiar with in one dimension, which is fx equal to x cube, or just x1 cube. And at x1 equal to 0, the gradient is 0, and the curvature is also 0, but clearly x1 equal to 0 is not locally minimum. So then when can we say that x star is definitely optimal? If grad f of x star is 0 and S transpose strictly greater than 0 for every s except s equal to 0, 0, 0. So take any non-zero s, and I'm able to show that for every non-zero s this strict inequality holds. Then x star is locally optimal or minimum. The book has a stronger theorem which says that when these conditions hold, then x star is isolated and strictly locally optimal. So we'll not go into the proof. The proof is quite short in the book, about half a paragraph or so, but it needs four main deep insights. One regarding the Taylor series, the other regarding eigenvalues, and two more small pieces. So we are not going to discuss this proof, and in fact many other proofs in the book, but you should try to read it once and go through it and try to get the gist out of it. So these are my sufficient conditions. So if these are true, then I'm done. If these two conditions are true, then I still don't know whether I'm done or not. But if these conditions are false, then I know for sure that x star is not locally minimum. So again, this condition is difficult to check because there are potentially infinitely many s vectors that we might have to try. So we don't check for this condition. Instead, we check whether and these two conditions are equivalent is positive definite. And that means eigenvalues of the Hessian at the current point are all strictly greater than 0. All. Not 1, not 2, all of them. There are also 2-3 more tests which you can do for positive definiteness. They are there in the book. Please try to go through them. Okay, so now if I come back to my algorithm, so while not converged, so I can replace this by saying while the gradient of f at the current point is still greater than some epsilon, I keep searching, and as soon as the gradient at the current point falls below epsilon, I will stop, because I'm and this will give me give us is very small, close to 0. We can't get absolutely 0 because of precision errors on calculators and computers. So we are happy if this vector goes sufficiently close to 0. So such a point where the gradient, a point where the gradient is 0, so we are talking about point x star, is called a critical point. So most algorithms will just search for critical points and then do a test for positive definiteness or positive semi-definiteness and stop there. Because once your gradient is 0, then your steepest descent doesn't tell us where to go next, because we were relying on the gradient to go in a direction of improvement, but if that gradient becomes 0, then there is no way I can move. So such points are where you don't verify whether they are optimal or not. They are called still called a critical point, and sometimes you might just want to stop at a critical point and move on. Sometimes you would like to check whether it is locally minimum or not. That's a good idea to check, and if it turns out that the Hessian is not positive definite, then it might be a good idea to do some more search in the neighborhood or somewhere far off to find a better solution. There could be other tests also besides this this test. So there could be a test which checks whether I am moving at all or not. So if my iterates become too close to each other, so these are n tests, one for each component of x, and if all of the components have very low change values, then also we can stop. That means we are not at all moving anymore, and maybe it's just time to stop. So this needs n parameters. You need to select these epsilons beforehand. This test needs only one epsilon, so it is somewhat easier to control. And you can think of more tests, something like fk minus fk plus 1 is less than or equal to epsilon. So if my function value itself has sort of tapered off and not moving too much, then also I should stop this algorithm. So this convergence or stopping condition is usually a mixture of these 3-4 criteria. One is the gradient being close to 0, the other is the magnitude of improvements in the function, and the change in the x values of the optimal solution. So stopping conditions combine the above. We still have to find out the alpha value. So remember that xi plus 1 is equal to xi plus alpha times s. Once I have found s, I still need to find this alpha. So that finding alpha is usually done by a method called line search. It's not an very formal method. It's a idea, and there are many ways of doing line search. We will just look at one or two of them. One can do an exact line search. In which I will try to find the minimum point on that line, or inexact. If I see good improvements, I will stop and move on, because most likely the optimal point may not be in this direction. So there's no point to exactly minimize along a candidate direction, because that's not the final direction. We will move a little bit, and then we will move again in some other direction, and so on and so forth. So these details we will look at in the next part of this lecture.